Okay, so in this section, in this video, I'm going to be exploring the world of differential equations, as the title says. Now at university level, this branches out so much more. You learn something called partial differential equations, second order, which we branch into further maths if you look at that. So in this course, in A-level maths, which is what this video is all about, you're going to look at differential equations. Now, we have met differential equations before technically, if you're doing it in the order of the textbook. You would have met already dy by dx could be equal, I don't know, 2x plus 1. Yeah, that's a differential equation, so it's got a dy by dx in it. You know, it's basic stuff, right? So how would we solve this? Well, to solve it, all we need to do is integrate both sides. Integrating dy by dx gives you y, of course, we know that. Integrating x squared, we get, integrating 2x, we get x squared, should I say, plus an x, plus the constant c of integration, as we know. Now this, in differential equations talk, we call it the general solution. So the general solution to this differential equation is this. However, well, this is not where this ends, of course. Of course it doesn't end here. Because you might want, for example, a whole section. There are tons of these parabolas. Yeah, but you might want just this one. A particular point, say, I don't know, 5, 5. Okay, so 5, 5, if we sub that into our equation we've got 5 is equal to 25 plus 25 plus c. No, it should be 5, sorry. 25 plus 5 plus c. So what we see, hopefully it's minus 25, done the calculations correctly. So we get y is equal to x squared plus x plus constant c, which we now can replace with minus 25. And this, in differential equations talk, is what we call a particular solution to the differential equation. So it's the particular one that we want. Now, that's what we meet in basic terms, what you've already seen. However, in this section, we're going to look at something like, say, dy by dx equal to now x times y. To solve that, we're going to use a technique in this section called separation of variables, essentially. Now, separation of variables means you get one set of variables on one side and one set of variables on the other. So to solve this, you divide by a y, multiply it by the dx, and integrate both sides. That's the way it solves that. So this is where you need your second year integration techniques. Differential equations is taught in the second year of A-level maths according to the EdXL textbook. I don't have the second year with me at the minute, but I will have it when I do some examples in a bit. Okay, so you divide by a y and multiply by the dx, that one. Okay, so that's what we're going to be exploring and looking at in this section. Now, if you're looking at further maths, this is a great starting point, but it gets harder than this, a lot more difficult in further maths, especially doing like FP1 for the pure, right? So if you want to explore the world of differential equations with me, stick around, because we're going to go through a lot more examples in this section. Okay, so we'll have a look at these 3 examples, each getting harder in difficulty. So we'll start with question number 1. Question number 1 is super simple. We've got its derivative being equal to x squared y. Separation of variables, need to get all one side and one the other, and everything on the rest. So we get 1 over y, dy, is equal to x squared dx. Basically treating the derivative as a fraction, which is really, really, really weird, I know, because we use it just as an operator, but we now are using it as a complicated function. And I have just dropped a pen lid. Excuse me. I'll pick that pen lid up. Okay, so with separated variables, brilliant. Next stage, integrate. So to integrate both sides, the left-hand side is nice and easy to integrate. Left-hand side 1 over y, just give me log of y. You can put modular signs in if you want to, you don't need to though. And x squared obviously integrates to a third x cubed, plus some constant c. Okay, so to get rid of the log, I probably want to e both sides, although this is perfectly fine. I just want to put it in a nicer form. Okay, so we get y is equal to e to the 1/3 x cubed plus constant. Indices laws, break this apart, times e to the c. Okay. Now each of the c is just another constant, we'll call it capital A for example, that's what we usually call it. We get a e to the 1/3 x cubed. And that is the general solution to question number 1. Look at number 2. We've got dy by dx, or is e to the y sine x. I'd put it on either side, it doesn't really matter, just to show you it doesn't really matter whatsoever. So I'll flip it around just to make it easy, because that's the form we've been used to getting it in. It's e to the y sine of x. Well, if we do 1 over e to the y is equal to sine x dx. Or integrate both sides there. Now 1 over e to the y, well what is 1 over e to the y? Any ideas? Well, don't forget, 1 over e to the y is just natural log of e to the y, isn't it not? Yeah? Gotta be careful. Sine x, what's the sine integrate to? Minus cos, I hope. Yeah? Because cosine integrates to sine, so sine integrates to minus cosine, plus a constant c. Okay, after we've done that, well, we can get rid of this negative sign by just multiplying everything through by minus 1. So we get e to the minus y is equal to cosine of x, plus, I don't know, some next constant, which we usually call capital A. So we get minus y is equal to logging of both sides, if you will, of log of cosine of x plus a. Well, what's log of a? Well, I don't really want to do any much with that at all. I can just bring the negative sign out, can't I, really? Oh, you get y is minus log of cosine of x plus a. Okay. And that is the general solution for number 2. I'll look at number 3 then. Have a look at that. I'll give you a minute to have a look. Okay, so hopefully I've had enough time there with that question. So question 3 then. 2y plus dy by dx is equal to y square root x. Okay, so we need to use our indices law, so write root x is x to the power of a half. So we get dy by dx. On its own, we'll take the 2y away, and I'll also write that as a power of a half at the same time. Okay, so we get to that. Now I can probably factor the y out, get y lots of x to the half minus 2, yeah? And obviously the dy by dx stays there as it is, just write it out in full. Then I can obviously now separate the variables, so I'll divide by y. So I can just integrate 1 on y dy is equal to x to the half minus 2 in respect to 2x. Obviously you need to bracket around that because it's more than 1, so when you integrate. Yeah? Well, 1 over y, we've just done that as log of y. Now this ugly beast, well, x to the power of a half is add 1 to get 3 halves, divided by that so you get 2/3 x to the 3 halves. Now minus 2 just improves to minus 2x, doesn't it now? We can add the plus c, then we can exponentiate both sides, getting the log e to the power of 2/3 x to the 3 halves minus 2x plus constant. Then I can break this apart, so we get y is equal to now e to the c is again, it's just another a doing it all in one step, so we get a e to the 2/3 x to the 3 halves minus 2x. There we go. Okay. And that is my general solution to the differential equation. Okay. So 3 examples, each getting harder in difficulty, as you probably can tell. And the hardest one you could probably get given is probably question number 3. This is probably the hardest one. Okay. So we'll have a look at more complicated examples in the next part of the section.
Got a nice little brain break for you on the way. We've got a nice little video of some nice calming seas as a little brain break. We'll get back to some particular solution differential equations in this.
Can't remember the last time my rain was out you. where do I go?
Okay, so the next part of the video we're going to look at these 3 examples here, each getting harder in difficulty. Excuse me. So we'll start with question number 1, of course. So the dy by dx is xy cubed at 0.11. Okay, separation of variables then. So we've got the integral of y to minus 3. Okay. Because you're dividing by it to bring it up to make a power of x dx. Okay. Got y to the minus 2 over minus 2. I'm just now doing the integrating bit. Plus constant c. Rearrange it, make it a bit nicer. Get y to the minus 2. From minus 2 you get minus x squared plus some constant a. Some new constant now. So this is your general solution. Well, at 0.11, sub that in there. We got 1 is equal to 1 over a, take away 1 squared, which is 1. So you get a minus 1 is 2. So your particular solution to the differential equation is 1 over 2 take away x squared. That is your particular solution. Okay, that is question number 1. Question 2 is harder in difficulty. Okay, have a look at number 2 then. So dy by dx is y plus 1 over x plus 1. Okay, if I get 1 over okay, separation variables done. As we were. Next, integrate both sides. Easy bit. Okay. Now, funnily enough, that's the general solution. I don't need to do anything with that at all. But I'm going to sub in that point now to 3. X is 2. And what is it? Y is 3. Yeah? 3 plus 1 get log. 4 is log of 3. Now, these using log laws basically here. C is log 4 take away log 3. Well, using your log laws, it's the same with natural logs. Subtracting logarithms, you divide whatever's in the bits. So you get a log of 4/3. Sorry, that's right to the edge of the board there. Apologies for that. So we've got that bit now, so we can actually substitute this back in here. So we get log of y plus 1 is log of x plus 1 plus log of 4 over 3. Combine those using the log laws that we know about. So we'll get log of 4/3 x plus 4 over 3, which is log of y plus 1. Now we can just get rid of the logs. So we get y plus 1 is equal to this 4/3 bit, right? 4/3 x plus 4 over 3. So you can see what it's going to become. It's going to become a straight line. We get y is equal to 4/3 thirds x plus 1/3. Okay? And that is my particular solution to this differential equation. Question number 2, yeah, it is. Question number 2. Next one, I'm going to look at question 3. Now, question 3 is absolutely nasty, isn't it? Let's have a look. So the dy by dx is y cubed plus 1 loss of cosine x all over y squared, evaluated at pi over 2, 5. Okay, I'll give you a minute to think about it, and then we'll have a look at it. Okay, should have enough time there now. So, if you've had a look at this one already, then you know basically what's got the comment is basically separation of variables. So, we've got y squared, or y cubed plus 1, so separating the variables. Multiplying by the y squared, dividing by that is equal to just cosine x, isn't it? Plus, just cosine x dx. Dy. It's great. Hopefully you can still hear me, by the way. So, we've got this. So, we've got 1/3. Now, integrating that, you could, if you wanted to, use u substitution and use integral substitution. However, because you've not done that yet, and inclined, you probably just want to use a log trick. The log trick for that is you've got exactly 1/3 of what you need. So you've got log of y cubed plus 1 times 1/3. Okay, it's quite clever. In cosine, obviously, it's raised to sine x plus a constant c. Okay, now you could probably multiply by the 3. You could do that just for log of y cubed plus 1 is 3 sine x plus some new value now a, and that is my general solution to this differential equation. At pi over 2, 5, so evaluating at that, you're going to get subbing in 5 cubed, well 5 cubed is 125, plus 1 is log of 126. Yeah? Is 3 sine of pi over 2. I have to work out what sine of pi over 2 is in a minute. I have to add on a, of course. Now, sine of pi over 2, if you can remember what sine of pi over 2 is, it's quite nifty because 3 lots of that will just give me 3. It's quite neat, actually. So it's actually 3 plus a. Okay. So a is a log of 126 take away a. Well, not take away, it's take away 3 in it. Apologies, like that. Okay. So the particular solution to this differential equation is log of y cubed plus 1 is 3 sine x plus log of 126 minus 3. And that is my particular solution to the differential equation. Okay? Not challenging at all. This is not a challenging concept. It's just getting used to that technique of separation of variables. Okay? A reason why that actually was quite neat, if you were wondering, sine is pi over 2 is 90 degrees, right there. So it reads off at 1. All right. So just if you wanted confirmation that pi over 2, sine of pi over 2 is equal to 1. There's your confirmation. Okay, so that's the end of this video looking at particular solutions of tough differential equations. This is just a little intro. I'm going to put a separate video out at a later date looking at forming differential equations and ended up solving them in real life situations. So for example, you can model a differential equation with water running out of a sewer, or the volume of water in a tank as it decreases as it's being used, so we can look at stuff like that. And you can look at differential equations with height, so dh by dt, in different parameters. Of course, we'll get to that soon, so I'm going to go and have a nap, and I'll let you practice some differential equations from your textbook of choice. Okay, so thanks very much for watching. Don't forget to like and subscribe. Hopefully you're pretty confident with this, and it's just a little bit of practice that you need to do well and succeed in your exams. Best of luck. with all the exams that you got to do, especially this one before Christmas, which is kind of annoying for teachers that have to mark them, you know what I mean? And of course, they've got exams in the spring and the summer. I might film a separate video about that. If you want to film a separate video about the 2022 exams, let me know. And then obviously I'll do the exam papers once they are released on the website for 2022. Okay, 2019 papers, I'm currently working through those. They'll be released soon. Okay, so that's what we'll look at, and that's where we're going to end this video. Thank you very much, goodbye.